Imagine you are standing on the deck of a massive wooden ship in the middle of a dark, stormy Atlantic Ocean in the 17th century. The wind is howling, giant waves are crashing over the sides, and thick fog hides every star in the sky. You have no GPS, no radar, and no digital screens. If you guess your speed wrong by just a fraction, your ship will crash into hidden rocks, killing everyone on board. To survive, sailors abandoned the concept of land miles and traditional clocks. Instead, they dropped a wooden log tied to a rope directly into the raging sea. Welcome to the subject history. Today, supertankers carry billions of dollars in cargo across the oceans. Commercial jetliners fly millions of passengers through the sky at 30,000 feet, and nuclear submarines navigate silently through the abyssal depths. Yet, if you look at the cockpit instruments or the navigation bridge of any of these modern machines, you will notice an odd detail. They do not measure speed in miles per hour or kilometers per hour. They use a unit called knots. Using standard land measurements in the sky or at sea invites a high risk of navigation error. The reason we still use this maritime unit comes down to a specific mathematical link between the ocean, the sky, and the exact shape of planet Earth. Centuries ago, as global trade expanded rapidly, empires faced a deadly logistical crisis. Navigators could easily measure how far north or south they were by looking at the stars. But measuring forward momentum across a featureless ocean was nearly impossible. On land, you can place a physical milestone and measure the distance between two static points. On the open ocean, the water is a constantly shifting surface moving underneath you. The solution came from an ingenious piece of equipment called the chip log. Sailors took a wooden board, attached it to a long rope, and threw it off the back of the ship. The wood was designed to bite into the water and stay relatively still, acting as a temporary anchor point while the ship pulled away. But knowing distance is only half the equation for speed. You also need to measure time. Doing that in the middle of a storm without a modern watch presented a second massive hurdle. The crews solved this by standardizing their timing with an hourglass filled with sand, calibrated to run out in exactly 28 seconds. To count how much rope pulled out during those specific 28 seconds, the sailors tied literal, physical knots into the rope at precise, equidistant intervals. A single sailor would hold the line, feeling and counting the knots as they violently slipped through his fingers before the sand ran out. If 10 physical knots slid through his hands during that window, the ship was recorded as moving at a speed of 10 knots, turning a survival trek into a standardized maritime system. Navigation was transformed when cartographers synchronized the spacing of these knots with the mathematical grid of the Earth. A standard mile on land is an arbitrary distance. It was originally based on 1,000 paces taken by a Roman soldier. It has no direct relationship to the planet itself. Earth, however, is a sphere. Cartographers mapped this sphere by dividing it into a grid of 360 degrees of latitude and longitude. To track precise locations, scientists divided each single degree into 60 smaller parts, known as nautical minutes. When designing the nautical mile, they made it equal exactly 1 minute of arc along the Earth's curve. Looking at this nautical chart, the utility becomes obvious. Because a knot measures exactly 1 nautical mile per hour, it directly links the vessel's speed to the physical grid lines on the map. If a pilot or a sea captain travels at 30 knots for 1 hour, they know with absolute mathematical certainty that they have traveled exactly 30 minutes of latitude on their chart. There is no complex math required, there is no unit conversion needed, and no deadly human errors introduced while trying to calculate distance in the cockpit. Advanced satellite networks now guide our journeys, but the humble knot remains the standard. It provides a direct link between physical movement and planetary geometry. If you enjoy investigating the technical history behind everyday life, follow the subject history. Every week, we examine the specific origins of the systems that define the modern world.